Hi everyone, so in the previous discussions, we have discussed their methods in modeling our structures. But our models, how complicated it might be, would still have no or very little use if there are no loads subjected to it. So from that guys, in this video, we would be having a little bit of a background or an overview of sorts regarding the loads that we will be assigning to our structures. Okay, so speaking about loads, so when we are to talk about loads in structural engineering, we would stumble across these common terminologies. So I would just be writing them here. So when we are to talk about loads, once again, in structural engineering, we would be stumbling across these terminologies right here. So we would be having gravity loads and the other being lateral loads. So what are to be these two terminologies right here? So when we say gravity loads, these are to be the loads or the forces that is acting along the direction of the gravitational pull. So when we say that they are acting towards the direction of the gravitational pull, it is directed to the center of the Earth. So that is by the name itself, so gravity. So by that guys, when we say going to the center of the Earth, this is basically vertical in nature. So vertical, so that is for your gravity loads. And since your gravity loads are to be vertical in nature, so that means that your lateral loads are to be horizontal in nature. Okay, so in this video guys, we would be focusing mainly on dead loads. So dead load, live load, so these two right here are to be your gravity loads. And as for our lateral loads, we would focus mainly on earthquake loads or our seismic loads and our wind load. So there. But first things first guys, let's go straight to dead loads first. So when we say dead load, so I would just be writing them here first. So dead load. So your dead loads are actually structural loads of a constant magnitude over time. So with that guys, what I mean there is that your dead loads are permanent in nature. So they include the following but are not limited to. So you have the self-weight of your structural members. So let's say your beams. So beams, columns, slabs, ceilings, let's say ceilings, roofing, and whatsoever. And they also include some fixtures which are basically permanent in nature. So let's say that your toiletries, I mean your toilets, your showers, your bathtubs, and whatnot, as long as it is permanent. And with that guys, if your dead loads are to be your permanent loads, your live load, so your live loads are, I mean in civil engineering, are a term that refers to a load that is not constant over time. So they are loads that can change over time, or your temporary loads. So this consists of the following, but once again not limited to. So occupancy of the building. So by occupancy, these are to be us, or these are to be the people walking inside the building, or the occupants itself. And what else? So this also includes the furnitures and others. But here in live loads, guys, this can be categorized into two. So we have our floor live loads and the roof live loads. So we will be discussing this later on. But once again, going back to our dead loads. So these are to be the loads that the NSCP has provided, or the National Structural Code of the Philippines. So by the way guys, if you would be looking below me, that is to be our reference material for this video, and that is to be the 2015 edition of the National Structural Code of the Philippines. So ayun. Okay, so once again, these are to be some of the minimum densities and the pressures that the National Structural Code has provided. And once again, these load densities and pressures are as follows but are not limited to. So for example, that you would be having a certain masonry brick material as your dead load. This is to be its density in terms of kilonewton per cubic meter, or our unit weight. Or let's say that we would be using aluminum for a certain material, I mean for a certain component of our building. This is to be its unit weight per unit volume. Okay, so there, and these are to be the pressures for our dead load. Let's say that we would be using an acoustical fiber board for our ceiling. Then we would be having 0.05 kilonewtons per square meter pressure. So there, and looking at this part right here, this is for your concrete masonry units or your hollow blocks. So these are to be its loads, its thickness, and its specification, whether it is to be grouted, not grouted, and anything in between. So ito yung mga gagamitin natin. Moving forward, let's go to live loads. So these are to be your floor live loads. So floor live loads. So what are these floor live loads right here? So these are to be the combination of both the occupancy load and the furnitures though. So both of them are already taken into consideration. So for example, that you are to be designing a certain residential building. So if you would be looking here, this is to be for the residential building. So for the basic floor area, so this would consist of your living room, your kitchen, your bedrooms, and anything in between. So you would be using 1.9 kilopascal of load. But take note guys that these are only to be minimum. So minimum lang yung itong 1.9 na to. So hindi tayo pwedeng bumaba dyan, pero pwede tayong mas mataas. So for example, that in that certain residential building that you are designing, medyo nahuhulaan yung medyo mas mabibigat yung tao, or let's say that it would be denser than most houses, you can use 2.5, 2, 2.1, anything higher than that, just not lower than 1.9. So there, and for example that you are to design that certain residential building to have an exterior balcony, so ito yung gagamitin naman natin ngayon. So we would be using 2.9 kilopascals and whatsoever. So for example, you want to design a certain school, and in that school, you are designing its ground floor corridors, then you would be using this pressure right here, which is 4.8 kilopascal. So that is for your floor loads. But take note here, guys, that your restrooms, so as you can see, this is for your restrooms. Oops, sorry. So this one right here is for your restrooms. So it does not have any load. But if you can see in this note right here, I'm not quite sure if you can read it, but if you have your NSCPs with you, it is to be at the bottom part. It is said there that for your restrooms, loads shall not be less than the load for the occupancy in which they are associated, but need not exceed 2.4 kilopascal. So meaning that you would be using, you would be designing this restroom in a residential building. So if its basic floor area is to be 1.9 kilopascal, meaning you would be using 1.9 kilopascal here. Or let's say that you would be using for your office. So in this one right here, it is said that for your offices, for call centers and business processing office, your uniform live load is to be 2.9 kilopascal. So the question is that, would you use 2.9 here? So the short answer to that is no, because we have a maximum load here, which is 2.4. So this one right here is to be 2.4. So meaning you would be using 2.4 here, since 2.9 is greater than 2.4. So that is for your floor live loads. So moving forward, we would be having our roof live loads here. So these are to be their minimum roof live loads. So for our roof live loads, it is dependent upon the slope of the roof and the tributary area of the roof. So let's say that we would be having a certain roof. Of course, it is slanted. So meron siyang slope, no? So kunin mo yung rise over run. So let's say this is to be your rise and this is to be your run. So y divided by x. And as you can see in the left part of your screen, this is to be in terms of percentage. So from that, guys, multiply nyo lang to ng 100%. So if you would be multiplying them, you would be arriving at an answer in percent form. And from that, guys, you would be choosing from this tree right here. So if it is less than 33.3% slope, you would be using these pressures right here. Let's say that your slope is between 33% and 100%, you would be using this. Or if your slope is greater than 100%, you would be using these ones right here. But the question is, which of these pressures right here would you use? So if you already know the slope of your building, the slope of your roofing, the next thing that you would be doing is that you would be getting the tributary area of that roofing. But take note, guys, that even though that your roofing is to be slanted in nature, So kapag slanting nga siyang ganito, your tributary area is not to be this particular area right here. It is not to be the slanted area. It is, it should be the horizontal projected area. So it would be this one right here. So ito yung tributary area dyan, and ito din tributary area sa kabila, and whatsoever. So let's say that you have chosen this, and let's say that your tributary area is to be between 20 to 60, then meaning that your pressure that you would be using for your roof live loads is to be 0.7 kilopascal. Okay, so there. And once again, guys, even if that your roofing is to be sloping, these are to be a gravity load. So meaning that they are directed vertically downwards. So what do I mean here? So once again, for example, that this is to be your roofing. And let's say that you would be having a certain pressure. So for example, ito nga yung pressure niya. Your pressure is to be like this. So ganito siya. So it should be vertically downwards. But of course, syempre nakadikit siya sa roofing. It's just that in your computations, it should be like this. So parang ganito lang siya kasi yung kukunin mong area niya is to be the horizontal projection and not the slanted projection. And even though in this diagram right here, this live load is floating, of course, yung live load natin sa bubong, hindi naman yan lumutulutang. So ayan, so that is to be this roof slope right here. For your roof live loads right here. Pero nakakatawa, no, pati yung ating table, meron din siyang slope. Anyway, so that is for your dead loads and for your live loads. So let's go straight to our lateral loads, since that is to be our major concern here, since our dead loads and our live loads are easy peasy lemon squeezy. So wind loads na agad tayo. So once again, your wind load is a lateral load. And your wind loads are to be forces that acts on the parts of the building exposed to wind intensity. So for example, that we would be having a certain structure here. So let's say that this is to be your structure. So let's say that this is to be your structure. And let's say that there was a wind. So kunwari humangin. Then yung hangin tumama sa building mo. And that right there is to be, of course, your wind load. So it could be as simple as that. Kung hinangin yung building mo, so of course that is to be a wind load. And our base equation here, or the pressure that we will be using in our wind loads, is to be given by this expression, which is, so Q, or the pressure at mean height level, so let's say QZ, that is to be equal to 0.613 KZ, KZT, KdV squared. So as per these ones right here, let's tackle that later. So let's go straight to earthquake first before going back to wind loads. Okay, so once again, for your earthquake loads, earthquake is a sudden release of stored strained energy in Earth's crust that creates seismic waves. So that is by definition. But in structural engineering, guys, earthquake energy is transmitted into your structure in the form of a load which we call base shear. So for example, once again, that we would be having a certain building or a certain structure. Earthquake in structural engineering, or the earthquake energy in structural engineering, is transmitted to the structures in the form of a lateral load which we call base shear. And this is to be your base shear, or the shear at the base of your building at the ground level. So let's say that that is to be your base shear, and let's say that your base shear is to be given by the variable V. So there, and since this is to be your force V, of course, we would be having corresponding loads per floor. So we would be having this load right here, this load right here, and this load right here. And if you would be getting the summation of all of these loads, it should be equal to your base shear. So there. And how can we solve for our base shear, guys? So for us to solve for the base shear, it is given by these equations right here from your National Structural Code of the Philippines. So I forgot what page this is, pero that is 208.5.2.1, or the design base shear. So it is stated here that the total design base shear in a given direction shall be determined from the following equation. So basically guys, this is to be your base shear. So that is to be given by CV times I divided by RT times W. But take note guys that the total design base shear should not exceed the following. So meaning that this is to be your max base shear. So this is to be your maximum base shear. And it is also said here that the total design base shear shall not be less than the following. So meaning this is to be your minimum. Okay, so in addition for seismic zone 4, the total base shear shall not be less than the following. So once again, this will be your other minimum base shear if ever that your structure is to be located in seismic zone 4. So what is this seismic zone 4 right here? So our country or the Philippines is to be divided into two zones. So for example, that your structure is to be located at this part of the Philippines. So let's say that it is located here. So meaning it is to be zone 4. But let's say that you would be constructing a building that is located at this portion right here. From that itself, guys, it is already to be in zone 2. So we only have two zones here in the Philippines, that is to be zone 4 and zone 2. Okay, so moving forward, guys. So these are to be the variables that we will be using in our equation. So we have here your V. Of course, that is to be our base shear. We also have our NA, or our NA is to be the near source factor. So what is this near source factor right here? It is to be given by this table. So that is to be table 208-5 and 208-6. That is to be NA and NV. So these are to be our near source factors. And this table, guys, is to be dependent upon the seismic source type and the closest distance to the seismic source. This is to be the distance from the structure to the nearest fault line. And what are to be the fault lines? So in our structural code, or the National Structural Code of the Philippines, we would be having this map right here. And this map right here shows the active fault lines here in the Philippines. So for example, guys, that I would be zooming in here in another table. So once again, this is in the National Structural Code of the Philippines. And these are to be the distribution of active faults in CAR, or in Cordillera Administrative Region. And since I am from Baguio City is to be located here. So we'll just be changing the color. So Baguio is located here. So there, and by visual inspection, guys, I can say that the nearest fault line is to be the Tubao fault, or the Tubao fault. It is to be this one right here. So if hindi nyo mabasa, okay lang. Hindi ko din mabasa. Pero check nyo na lang doon sa mismong libro nyo, because zoom in ko lang to, so medyo naging blurry na siya. Okay, so since that is to be your Tubao fault, what you would be doing is that you would be measuring from this point, or from the location of your project, to the Tubao fault, to the nearest fault line, which is to be this one right here. So after locating that, now measure it. So after measuring it, multiply its proper scale factor right here. So we have this scale right here for you to know how many kilometers it is from your project to the nearest fault line. So once that you have plotted it, you will be choosing it here. Okay, so moving forward, what are to be the seismic source types right here? So we have, once again, seismic source type A, B, and C. So it would be mentioned in this particular table right here. So this is to be table 208-4, or the seismic source types. So for your seismic source type A, these are to be located near the faults that are capable of producing large magnitude events and that have a high rate of seismic activity. Or let's say that your maximum moment magnitude are between 7 and 8.4. And for example, that the faults near your structure is not capable of producing large magnitude earthquakes and that have a relatively low rate of seismic activity. So from that, guys, you would be using seismic source type C. And if it is either A or C, you would be using B. So once again, that is for this one right here, for you to determine your near source factors NA and NV. Okay, so since we are done with V, NA, NV, we would be going straight to our CA and CV. So your CA and CV would be given by this table right here, which are to be tables 208-7 and 208-8. Okay, so as you can see here guys, our seismic coefficients here are dependent upon the zones, the near source factor, and the soil profile type. So this column right here are to be for your zone 2, and this column right here are to be for your zone 4. So how can we know in what row we will be getting our data here? So we have our soil profile types SA up until SF. So that is to be given by this particular table right here, which is table 208-2, or our soil profile types. So once again guys, this is in the book of NSCP. So for SA, this is to be for your hard rocks, SB rocks, and whatever follows. So these are to be its shear wave velocity, its standard penetration test, and its undrained shear strength SU. So there, and once that you already know what is to be the soil profile type of the founding ground, you can now check for its seismic coefficients here. So that is for your CA and CV. So what are these two remaining right here? So you also have your period of vibration and your overstrength factor. So your period of vibration here guys is basically the time for one vibration of the earthquake that is dependent upon the property of your building. Okay, so how can we solve for this T right here? So you can solve for it using these equations right here in 208.5.2.2 or the structure period. So we have two methods in solving for our period. So this is to be your method A and this is to be much more simpler. And for your method B, you would be using this equation right here. And as you can see, this equation right here is to be more complicated than that of this equation right here. Okay, so for method A, guys, this is to be given by, so your period T is to be equal to CT times HN raised to 3/4, whereas your CT is to be these values right here, and your HN is to be the mean height of your building. Okay, so for our steel moment resisting frames, you would be using 0.0853 for your CT. For your reinforced concrete moment resisting frames, you would be using 0.0731. And if it is either a steel moment resisting frame or a reinforced moment resisting frame, you would be using 0.0488. And alternatively, guys, you can also solve for CT as 0.0743 divided by square root of AC if your structure has a concrete or masonry shear wall. So if it has a shear wall. And this AC right here is to be given by this particular equation right here. So nakikita nyo guys, puro equation siya. So you are not required to memorize this equation since it's already in the National Structural Code of the Philippines. And truth be told, they are still subject to changing. So they are subject to revision every time na maglabas yung NSCP ng bagong revision. So there is a chance, although its chance is very little, may chance pa rin na mapalitan tong equation na to. So ayun, so it is of paramount importance for structural engineers or civil engineers to have their own copies of the National Structural Code of the Philippines. Okay, so that's how you would be computing for your structure period. Okay, so since we already know all of this, except with letter R, so the next thing that we would be doing is to get what letter R is, or our variable R. And our variable R is to be our overstrength factor, and this is to be given by this table right here in table 208-11. So once again, this is in your NSCPs. So going to that page, so it would be this one right here. So this is to be table 208-11A, or the earthquake force resisting structural systems of concrete. So a little bit of an emphasis here. So concrete, so meaning guys that these parameters right here are only applicable for a concrete structure. So for example, that you are to be designing a certain steel structural system, you would be going to the next table, and the next table is to be this. So earthquake force resisting structural systems of steel. So it is to be given by both of these tables right here. But for example, that your earthquake force resisting structural system is to be of concrete nature, of masonry nature, I should say. So you would be using this table. And if you are using wood, then you would be using this table. let's have an example here. So for example, that our structural system is to be a concrete one. From that, guys, we would be using this table right here. And let's say that our building is to be a special moment resisting frame. So the next thing that you would be doing is that you would be searching for the special moment resisting frame right here, or our SMRF. So where is it? So it is to be this one right here. So special reinforced concrete moment frame. So with that, guys, our R, or our overstrength factor, is to be 8.5. So there. And how can you say that your structure is to be a special reinforced concrete moment frame? You can evaluate it this way. So if your building, of course, if your building is to be made out of concrete, it would be having certain joints. So let's say that this is to be your column, this is to be your beam, this is to be your beam, and this is also to be your column. Of course, we would be having particular moments here. So in your column moments, you would be having a certain moment here. So let's say that that is to be MC. And of course, we would be having another moment here. This is to be also MC. And for your moment of the beam, so it would be this one right here. So MB. And also this one right here to be at an equilibrium. So MB. So in this joint, guys, you can only say that your structure is to be a special moment resisting one if the summation, so the summation of your moments of the columns divided by the summation of moments of the beams should be, is greater than or less than 1.2. So if it does not satisfy this equation, so meaning that your structure is not of a special moment resisting frame, so SMRF. So once that this parameter right here, this condition right here is satisfied, so meaning that your structure is qualified to be a SMRF. Okay, so what does SMRF mean? So your special moment resisting frame. So it means that the frames are to be the one that will be carrying the lateral loads. So kapag may lateral loads tayo like yung earthquakes, yung frame natin yung pipigil sa kanya. But for example, we would be having a certain dual system. So yung dual system natin is to be the combination of both SMRF and ang ating shear walls. So that is, so this one right here, 25% of the lateral loads would go to the frame and 75% of the lateral load will go to the shear wall. So, ganyan. So, kanya-kanyang research tayo dito sa mga ibang ito. Okay, guys. So, I almost forgot. So, we have established the meanings of these variables right here. So, V and A up until R. But I forgot to include this one right here. So, this is to be your letter I or your variable I. And your variable I is basically your importance factor. So, importance factor. So this importance factor right here indicates how important your structure is. So it is to be given by this table right here. So for example, that your building is to be an essential facility, you would be using this seismic importance factor I. And let's say that you would be having a certain standard occupancy structure. So these are to be for your residential buildings. This is to be 1.0. So ayun. Okay, so with that, guys, you now have our base shear. So we already have all of these parameters, then solve for all of these equations, then check which base shear would govern. Okay, so once that you already know the base shear, so the next thing that you would be doing is that you would be distributing them to each of the floors. So you would be using this equation right here, which is, which are to be the following. So 208-15, 208-16, or 208-17. But I will be teaching you on how to use this 208-17. So here, so for example, that this is to be, where will I put this? So let's say that here. So this is to be our equation here. So let's say that this is to be fx. So let's say that this is to be f1, this is to be f2, and this is to be f3. We can solve for this f3 right here using this particular equation right here. So your f3 given once again by this particular equation right here is to be equal to your base shear. So your base shear is to be this one right here minus Ft. So minus Ft. So what is Ft? It is to be given by this equation right here. So you can solve for this one. So ito. So minus Ft times Wx. So times Wx times Hx. So your Wx is to be the weight in that floor. So since we are solving for F3, so this is to be your W3. So whatever is the weight of your third floor. So this is for your W3. Sorry, this should be W3 and H3. And H3 is to be this height right here. So from the ground up until the level that you are analyzing. So divided by the summation of all of them. So this is to be your W1 F1. So of course, we would be having a corresponding weight here. So this is to be your W1. And you also have your W2 here. And whatsoever. So that is for this one. So in your denominator part, you would be multiplying your H1 and your W1 plus your H2 times W2 plus your H3 times W3. So that is for the denominator side right here. So there, and for example, that you want to know the value of your F2, you would just be changing this one right here to W2, and you would just be changing this one right here to H2. So it would be as simple as that. Okay, but later on guys, in our STAAD softwares, what we would be doing is that we would be inputting all of these parameters right here, and that we would be checking if it is accurate with our National Structural Code of the Philippines, which of course would be the case. Okay, so that is for our seismic loads. Okay, so for our wind loads, guys, we would be making use of these steps right here from figure 207A.1-1. So these are to be the steps. So what you would be doing is that you would be getting the basic wind speed, the wind directionality factor, the exposure category, and whatsoever. And once that you have computed for your Q pressure right here already, you would either be getting the wind loads on the MWFRS or the CNC. So your MWFRS here is to be your main wind force resisting system. So there, and as for this one right here, this is to be your components and claddings. So your components and claddings are to be your components that are not really resisting the wind for your system, if I'm making sense here. And as for your MWFRS, of course, these are to be your resisting components. Okay, so once again, the first thing that you would be doing here is to solve for your pressure Q. So Q, once again, is to be equal to 0.613 kz, kzt, kd, and v squared. So what are to be these parameters right here? So your v squared right here is to be your basic wind speed. So this is to be in meters per second. Your kd is to be your directionality factor. Your kzt is to be your topographical factor. And kz is to be your zoning factor. So let's go from page to page. So for your v squared, guys, or for your v, you can just check them here. So for example, that you're analyzing for a certain structure with occupancy category 1. So what is occupancy category 1? So your categories or your occupancy categories are to be given by these tables right here. Okay, and once again, this figure right here is for occupancy category 1 building. So what is to be your occupancy category building 1? So those are to be your essential facilities. So ano siya, it is either your hospital, your public school building, aviation control towers, your fire and police stations, garages, and whatsoever, as long as it is in this definition right here. And for your residential buildings, that is to be occupancy category level 4. So there, this is to be it. So once again, this is to be the map or the figure for you to know the basic wind speeds if you are analyzing an occupancy category level 1 building. Okay, so as you can see here guys, so let's say that your building is to be located at this portion right here. So what you would be doing is that you would be reading this one right here. So if you cannot read that, it is okay. I cannot read it either. Pero assuming, kung tama man nakita ko, 280 ata yan. So this is to be in terms of kilometers per hour. So 280 kilometers per hour. Ata. So I'm not quite sure because I cannot read it either. But for us to be sure, just check on your National Structural Code of the Philippines na lang. Okay, so that is for your V. So what you would be doing here is that you would be converting it into meters per second. Okay, so one down. So we already have our value for V. How about for the others? So we still have KZ, KZT, KD. So what is for KD? So basic. For your KD, it is to be given by this table. Mamili ka lang dyan. For example, that your building is to be a main wind force resisting system. It means that your KD or your directionality factor is to be 0.85. So that is for KD. What about for KZT? So your KZT is to be given by this equation right here. But correct me if I'm wrong guys, but I think that this is erroneous. Because according to ASCE, your KZT is to be equal to 1 plus K1 times K2 times K3 squared. So I think that this is to be more accurate than that of this one right here. But so there. And I think that this is to be an error or an error in printing. So typo lang ata ito because I really think that this is to be the equation that is accurate. Because if you would be looking at this table right here, so K1, K2, and K3, so these values right here are from these values right here. And it is said here that K1 is to be a multiplier, K2 is to be a multiplier, and K3 is to be a multiplier. And what do you do in multipliers? You multiply them and you do not add them. So from that guys, ito siya. 1 plus K1 plus, 1 plus K1, K2, K3 squared. Okay, so there. And where did this come from? So saan ba nanggaling itong mga values na to? It came from this particular equations right here. And this table right here, of course. So if, for example, that the location of your building is to be located at a 2D ridge or a 2D escarpment or a 3D asymmetric hill, so dyan nyo pipiliin ngayon kung ano man yung value na applicable sa inyo. And what are to be those? So for your escarpment, ganito siya. And for your 2D ridge or 3D asymmetrical hill, ganito siya. So ayun lang yan. Okay, so lastly, since we already have all of this, so we already have your KZT, KD, and V squared, the next thing that we would be solving is to be KZ. But take note guys that the order in which variable you should solve first does not matter. So ako kasi dibang ginawa kanina, sinolve ko muna yung V, then yung KD, KZT. So it does not matter if you would be going from KZ to V. So from KZ, KZT, KD, and V squared. So it really does not matter. So ayun, so once again, ang kulang na lang sa atin ngayon is to be yung KZ natin. So for your KZ guys, KZ is to be given by this equation right here. If your Z or the mean height of the structure, if it is to be greater than 4.5, you would be using this particular equation right here. But if it is to be less than 4.5, you would be using this equation right here. Whereas the value for your Z is to be the mean height of your structure. For the value for your alpha here is to be these values right here. And the value for your ZG is to be these values right here. And as for this exposure right here, it is to be dependent upon, once again, the location of your structure. So for your exposure B, these are to be your urban or suburban environment with closely spaced homes or home-sized buildings. So once again, these are all in your National Structural Code of the Philippines. And as for your exposure C, these are to be generally open terrain with scattered obstruction less than 30 feet tall. And as for your exposure D, so this is to be the most exposed of all. So they are to be flat, unobstructed areas just like your shorelines, yung mga nasa beach natin. Pag direkta yung hangin sa kanya, that is to be exposure D. So there.